Everyone. Good evening to all, and wishing you a happy Independence Day. So, I will start my presentation, and I I would like to present my project today based on the gravitational waveform emitted from the astrophysical object in eccentric orbits. Basically, in today's research on astrophysics, gravitational wave is treated as a signal from which we can study a class of astrophysical objects and phenomena. And its importance in the modern research is that there may exist some astrophysical objects which may be hidden behind some optically thick dust cloud. May there exist some uh, astrophysical objects. So by only electromagnetic signal we cannot detect them, right? So gravitational wave, we know that gravitational wave is not stuck between any optically thick dust cloud, so it can pass through it as a vacuum and can reach to us. So in that sense, gravitational wave is a very important uh, thing in the astrophysical research. So now I will like to analyze the gravitational waveform which emits from the eccentric orbits like circular orbits and elliptic orbits, and even from the hyperbolic encounter. And at last, I will turn my talk to the introduction to memory contribution. So here is the summary of the talk. To visualize the waveform pattern of the gravitational wave radiation from the inspiraling circular orbit, and also from the stable elliptic orbit. Again, to visualize the variation of strain amplitude of GW radiation with time in case of hyperbolic encounter, and thereby using the example of hyperbolic encounter, I would like to give a physical sense to the memory contribution of gravitational wave radiation. So let's begin with what is the gravitational wave actually. So our route of analysis is like, first we want to get some idea on gravitational wave. We want to picturize this. So first of all, you can see one second. You can see that G mu nu, which is the metric element to the to define the our line length of a line element. So this metric element is like equals to eta mu nu plus h mu nu. So what is our eta mu nu? This is the metric element for the flat space-time where no space or time dependent curvature. Okay, that is the simple -1 1 1 1. That's the eta mu nu metric. And we would like to treat the gravitational wave as a perturbation to this eta mu nu. It's called the h mu nu. It may be space and time dependent metric element, which is very small in order of compared to the eta mu nu. So adding this as a perturbation, we treat our G mu nu. So by this G mu nu, we can calculate the Christoffel symbols and the Ricci tensor, Ricci scalar, and using the Einstein equation, we get something. Thereby, the change of variable like this, where h is the trace of this metric, and using the harmonic gauge, we get this equation. So del square h mu nu equals to -16 pi g by c to the power 4 t mu nu, where t mu nu is the energy momentum tensor of from where the gravitational wave is observed. So by this, if you like to observe the signal from the vacuum, there is t mu nu equals to 0, because there is vacuum, there is no energy and momentum. So there is vacuum and t mu nu equals to 0, and this gives us del square h mu nu equals to 0. This is like our transverse wave equation. So that is the picturization of gravitational wave here. So now taking the t mu nu we can derive it simply by Green's function to get the h mu nu expression, where t minus x star by c is the retarded time, and the x star is the source coordinate and x vector is the position coordinate, sorry, the observer position coordinate. Then by taking the advantage of our harmonic gauge and the taking the advantage of symmetricity of t mu nu metric and looking for only t dependent part, I will come to this part now. First of all, consider the looking t dependent part. We get these two equation where h0 mu equals to 0 and hij equals to this type of thing, where the qij is defined as like 1 over c square t00 component xi xj d cube x in system. So it is computed at t minus r by c, that is retarded time. It is computed to get the hij metric at our time. So now actually there is some variable after taking the gauge condition. There is again some variables which if you are looking from the outside, that is there is only vacuum, so there at the vacuum there is t mu nu equals to 0. So looking from the vacuum, there will be more free parameters in the hij, so we can basically take the parameters by ourselves. Then so that is called the traceless transfer transformation. So for this transformation, we would like to introduce the Pij quantity, that is basically delta Ij minus Ni Nj, where Ni is the unit vector from the origin of the coordinate system towards the observer. So basically by defining like this Pij, we also define Pijkl by this Pij as Pik Pjl minus half Pij Pkl, and this is our traceless transverse operator. That is, we can call it the projector operator, which mainly trace out the hij metric and make it transverse. Also this h0 mu tt, which is trivial. So by applying Pijk on the Hij, this equation, we get this type of thing. Now I would like to get some questions if it's there. Neither I can take this as our master equation and proceed further to analyze the orbital systems. So is there any question up to this? Hello.
Let's keep the questions session at the last, if it's
Last
okay with
means,
you.
okay. So have you any question on up to this part?
Yeah, I can see one question in the chat. He's asking, what is HQS?
HQS, right?
Yep.
So it's basically the notation of the index, where if he or she can understand the h mu nu, which is the perturbation on the flat space time, that is so, then HQS is just a change in notation of the index. Is he or she like to share if he know the index notation of the tensor quantity? Okay, I think it's clear, right?
Yeah, yes.
Okay, so I think I can proceed towards the next slide. Okay, so taking this as our master equation, now we can move to the specialized system, that is a binary system. So first of all, what is a binary system? Binary system is basically two masses rotating around each other under their mutual gravitational attraction. So basically we know that we can visualize that system from the center of mass frame as a reduced mass rotating around the center of mass with the separation as the actual separation between the two masses. So we think of it as the mu rotating in a circular elliptical orbit in a radius r with the phi as a polar angle in the xy plane. So basically we can introduce the expression for the density of this type of system, mass density, which is mu delta x minus xt, delta y minus yt, and delta z. Delta z because it is only in the xy plane, nowhere else, and the mass is at time t. This is the position is xt and yt. So considering this as the expression for rho, that is the mass density, we can write the q components of the system, that is the quadruple components. See, rho is like t naught naught over c square, that is energy momentum tensor zeroth component divided by c square. We call it as the mass density. So there is qij equals to rho xixj dxj. So here you can see this. So in this xixj, we can put the position of the system. There is and using the rho, we can derive the qxs, qxy, and qyy components. Whether because delta z at z equals to 0, there is no qzi components. So basically, these are the non-vanishing components. Now taking the coordinate system as spherical polar coordinate, where r capital theta capital phi is the position of the observer. Uh, in the spherical polar coordinate system, we can change the qxs, qxy, qyy variable in q theta theta, q theta phi, and q phi phi variables. So in Cartesian to spherical polar coordinates, we can derive such expressions for these quantities. Now, in terms of traceless transverse mode, the quadruple moment can be written as q theta theta minus q phi phi, as you see here. So basically, now by taking the double time derivative of this quantity, we can determine the hij components of the gravitational waves. So basically you can see that these two quantities are same, and these two quantities are likely same with a negative sign. This quantity, the corresponding h for this quantity, it's called the plus GW plus polarized component of GW waveform, and corresponding to these two quantities, the h of the h is called the cross polarized GW waveform. So now we have to determine this plus and cross polarized ZW from amplitude, that is H plus and H cross, for the circular and elliptical binary up to this. So in case of circular orbit, there is two assumption for our simplicity, that is motion is maintained on Keplerian potential up to the merger. Uh, it's an assumption because we know that when two masses come very closer, their Keplerian potential is an incomplete expression for the actual potential. So we can thought this as a assumption. And the second one is InSpiral phase is approximated by circular orbits with decreasing radius. That is why this is an inspiraling. uh, I will come to that point. But considering first we consider the orbital is inspiraling, then the circular assumption is not maintained, right? But here, as the gravitational wave is a weak source of energy emission, so we can thought as when a circular orbit rotates very long time and then it shrink quite a bit. So we can think the E equals to 0 condition is maintained and the orbit is shrinking. So first fact that the R is a constant and phi is the omega t. So omega is constant in the 0th order approximation of InSpiral. By 0th order, I have meant that there is no gravitational wave emitted in the first. I mean in the 0th order, there is no perturbation on the system, and omega square equals to gm over r cube. That is, it's basically the Kepler's third law. We know. Then considering this, we can calculate the ZW polarization amplitudes as H plus equals to this and H cross equals to this type of things. Now basically there is one fact to note that binary have the angular frequency of rotation is omega, but here in contrast with the EM radiation, there is like 2 omega as the angular frequency of the GW waveform. That is an interesting fact in contrast with the EM radiation. And the amplitude is dependent on the omega to the power 2/3 factor. Okay, so now we come to the inspiraling of the circular binary. So what is why it's inspiraling? Because the gravitational wave is emitted and it should take out a certain portion of energy. So we can compute the energy loss per unit time using this formula, and we will get this type of thing where dEdt is basically dependence on v to the power 10. So we know that the total energy of a binary system is minus half mu v square. So from equating the dEdt of this with this, we can derive the orbital velocity with the time, as well as the omega and the radius of orbital with the time. So here you see that the radius is like decreasing with time. Here is the bracket, it's maybe misprinted. Here t is in the denominator, and thereby the radius of the orbit is shrinking. So and there we see that the time with the time the omega is increasing, because there is a minus sign in the power. So basically the order of radius shrinking is g cube over c to the power 5, which is very small in order of magnitude. And the time required for collision, collision mean when two point masses are basically when they collide, and they should collide after a finite time. This time is calculated as this. So basically it's not exact, because there is no merger condition, and the two masses are basically they have some radius which is initially considered and as the point mass. So this time required is not the exact quantity, but it's we can use this as an order of estimation. So by the way, omega is increasing with the time. So basically this type of waveform we should get as the gravitational wave, where we have know that the amplitude of the wave is increasing as power law omega to the power 2/3. So it's increased, and the gravitational wave ultimately omega goes to infinite. Then we should turn to the elliptic orbit, where eccentricity is between 0 to 1. So in case of elliptic orbit, the exact form of r as a function of t and phi as a function of t is not very analytically clear to us. So we can but here it is actually we can say something about this, because r and phi, basically these quantities are periodic with time. So we can make it a Fourier series of this with the omega, and we can use the as cos phi and sin phi, and these all quantities are written in the Fourier series, where W is the is omega t, right? Then using the Kepler's laws, we get the GW waveform amplitude in the Fourier series format. So basically we see that there is multiples of frequencies, that is n omega t. So basically in terms of Fourier series we get different I mean GW radiation from here is like polychromatic radiation uh, in contrast with the circular orbit, and there is some different amplitudes. The magnitude of the amplitude is written here. So basically we should show a graph. Here is the interesting fact: when eccentricity is very low, that is it going to be a circular, then we see that the h cross amplitude, which it is plotted with the h cross over h naught, normalized h cross, with uh, the Fourier components n. Here we see that the 2 omega t component is very high compared to other components. So basically it turns out to be the circular orbit when e tends to 0. And when we increase the eccentricity, we will see that the all other components are raising, and after the e equals to 0.42, we see that the competition is very interesting. And once more there is another point that all the amplitude, that is h cross over h naught, is first when e is very low, this is very high, and when we proceed with the eccentricity increasing, we see that all components are getting lowered. Here is the order of magnitude that we can see on the y-axis. Okay, so basically it is seen from the z axis of the binary, where I have written that the observation location is r observer 0 0. Now in case of hyperbolic encounter, there is something different, because it is not the periodic case, where here I define the phi naught as the epoch angle, and v naught is our initial velocity. So thereby, and quantities of motion we can calculate from the Keplerian laws in terms of the phi. Phi means the polar angle, and using this, and using the reduced quadrupole moment components, we see that the perturbation metric, we can calculate this as a double derivative of time, as we have done already. So the expected strain amplitude, we define the h as this kind of thing, which is h11, h22 means the h plus components, and the h12 is the cross component. And we can see, with variation of polar angle, the strain amplitude varies like this. So first when it start from the 0 0, that is the that is the starting point, and the ending point at polar angle pi by pi, and the motion ends here, and the maxima is like at 1.57, that is at pi by 2. Think at pi by 2, the test mass comes the most closer to the source point, and that's why there is a certain maxima where the gravitation is stronger, and the variation also happens. So thereby the gravitational wave is more stronger here. Then I should make a serious comment about this hyperbolic encounter, which is the memory contribution. That is, here we can see that we have not seen that the h11, h22, and about h12. So if we see these variation with the polar angle, that is the initial and the final, when the mass is an initial asymptote and in the final asymptote, we can see this h11 is basically higher than the final. Basically they do not same. H22 also is not same. H12 component is also not same. Basically it's 0 in the initially, and finally it is non-zero. So what can I infer from this? That is, Hij start is not equal to Hij end. Since g mu nu equals to eta mu nu plus h mu nu, and we know that g mu nu is a measure for the length of the line element. So basically, as Hij at start is not equal to Hij at end, so g at start is not equal to g at end. So there is we can infer that when suppose there is a rod of 5 meter, say, before the gravitational wave has passed through it, and after it has passed, when it passed through it, its length oscillates, measure of length oscillates, and when the gravitational ultimately pass through it, it becomes either 7 meter or 3 meter, as the uh, measure of the length has changed. So, and again, the interesting fact that dx dy appears at end because h12 component is not equal in measure of interval, which is initially was 0. So think as where if there is some like g mu equals to something dx square plus dy square, and then after that it becomes dx square plus dy square plus some dx dy, which includes which refers to a rotation of the measured coordinates. So this is the introduction to the memory effect. We can take as an with an example of this hyperbolic encounter. So basically this memory effect has been as like introduction. There is many different purposes of this memory effect, and hence moral of the all the story is like monochromatic radiation is emitted from the circular binary with the frequency twice as the orbital frequency, and during InSpiral, that is InSpiral happens as I said. So orbital frequency increases, hence amplitude and frequency of gravitational wave also increase. And the secondary result is the radiation is polychromatic from eccentric binary, where frequencies are in integer multiple of orbital frequency, and the non-periodic disturbance on flat spacetime due to movement in hyperbolic orbit, and also it turns out with a memory effect. And there is my future plan to study the gravitational waveform in merger and ring down phase of binary. Basically when two stars are colliding, this is called the merger phase, and ring down phase is when two suppose two black holes are colliding and they are mixed in a single black hole, then it's called the ring down phase. So and to study the gravitational waveform in post-Newtonian approximation of binary, I mean the where we should step a little bit ahead of the Keplerian things. And I also like to study on the memory contribution of gravitational radiation from binaries. That is, in case of hyperbolic, its linear is okay, but circular and elliptic, there is no memory contribution in first order of binary, but it is non-linear. When I calculate for non-linear case, it's certainly read some memory contributions. So basically this is all my topics. Thank you. Any questions or